Okay, in this video we are going to talk about a special kind of subgraph of a graph called spanning tree. So we will see the definition of a spanning tree. Then after that we will look at some one or two properties of spanning trees and some of the terms related to spanning trees. So let me start by defining a spanning tree. So a tree is said to be a spanning tree of a connected graph G. Okay, first of all, that subgraph must be a tree. Okay, so if T is a subgraph, okay, so let's call this tree T. So a tree T is said to be a spanning tree of a connected subgraph G if T is a subgraph of G and T contains all the vertices of G and T contains all the vertices of G. Okay, so a tree T is said to be a spanning tree of a connected graph. Okay, if T is a subgraph, so that's a first property that T should possess. Okay, T is a subgraph of G and T contains all the vertices of G. Okay, so let me give you an example of such a tree here. Okay, suppose that this is our graph G. Okay, so what I am going to do is I am going to highlight the highlight a spanning tree of this graph by in blue. Okay, so by definition, okay, it must contain all the vertices of G and that is a subgraph. Okay, and it must be a tree. Okay, for example, you could have something like this. Okay, so we included this vertex. Okay, so we included that vertex. Okay, this one. So here we can see that if we denote that subgraph by T, okay, T is a tree, it is acyclic and it is connected, and also we can see that, so here the total number of vertices is 1, 2, 3, 4, 5, 6, so 1, 2, 3, 4, 5. Okay, so here we can see that, okay, this T is a tree and that is a subgraph of this G, and moreover we can see that this T contains all the vertices of G. So that says, okay, this T is, okay, it is a spanning tree of G. Okay, so similarly a graph could have many spanning trees. For example, okay, another spanning tree, okay, of that tree may look something like this. Okay, so it must contain all the vertices and it is a subgraph. Okay, so now we can see that okay, this highlight one in orange corresponds to a tree and it contains all the vertices of the tree. Okay, so that says, okay, this tree is also a spanning tree. Again, similarly, let me draw two more spanning trees here. So another possible spanning tree could be like, start from here, you include this edge. Okay, from here you go to this one. Okay, from here use this edge. Okay, and from here use this edge and go to this one. From here I use this edge. Okay, so here again you can see that okay, this particular subgraph, it contains all the vertices, okay, of the original graph, and that is a tree, and it is a subgraph also, right? So here again you can see that okay, this highlight one, it is also a spanning tree. Okay, so let me draw one more. Okay, so let's consider, for example, say this one. Okay, from here you move to this one. Okay, from here you move to this one. Okay, and from here say you move to this one. Okay, and from here. Oh. So now you can see that if you look into this particular subgraph, that is a tree. Okay, it's a connected acyclic one, and also we can see that it contains all the vertices. Okay, so this violet subgraph, it is also a spanning tree. Okay, so in general a graph could have many. So this graph could have more than, okay, in this case we okay, show you 1 2 3 4 spanning trees, and it could have many. Okay, so anyway, that's a definition of what is called a spanning tree. So a tree is said to be a spanning tree of a connected graph G if T is a subgraph of G and T contains all the vertices of G. Okay, so let's look at one property of a spanning tree. Okay, so this particular statement talks about the existence of a spanning tree in a connected graph. So if we consider any connected graph, that graph has at least one spanning tree. Okay, so here we saw this particular graph is connected and it has many spanning trees. So this statement says every connected graph has at least one spanning tree. Okay, if the connected graph is a tree, then that tree by itself is a spanning tree. Okay, if that's not the case, then you could always find spanning tree in that graph. Okay, so let's go and prove this statement. So it's going to be a very simple proof. Okay, so in this proof we are going to use okay this statement. So we will prove this statement in a later video. Okay, so this statement says an edge E of a connected graph G is a cut edge or a bridge if and only if E is not on any cycle. Okay, if E is not on any cycle of G. Okay, so such a thing is called a cut edge, and this statement says an edge E of a connected graph G is a cut edge if and only if E is not on any cycle of G. So for example, if you look into this particular graph, you can see that okay, this is one cut edge. Okay, this is one cut edge or a bridge, and this is another one. So cut edge means if you delete that edge, the graph will become disconnected. So if you delete this edge, we can see that the graph will become disconnected. Okay, similarly, if you delete this one, we have one component here and another component here. Okay, so okay, these two edges are cut edges. So here again we can see that if you look at a cycle in this graph, okay, that cycle it does not contain a cut edge. Okay, that's what this statement says. An edge E of a connected graph is a cut edge if and only if E is not on any cycle. So here you can see that this graph has many cycles. So one such cycle is this one, okay, another cycle is this one, another is this one, and here again we have many cycles here. Okay, this one, okay, this one, and so forth. So you can see that if you look into any cycle, okay, it is not going to contain look at these cut edges. Okay, so anyway we will prove this statement in some later video. So we are going to use that here. Okay, that's why I mentioned here. So every connected graph has at least one spanning tree, and remember this particular theorem. Okay, so let's go and prove this statement. Okay, so let G be a connected graph. Okay, we can very easily see that okay, every connected graph has a minimal connected spanning subgraph. Okay, and let T be a minimal connected spanning subgraph of G. Okay, so minimal means if you delete one more edge, it will become disconnected. Okay, so that's what this minimally connected means. Okay, so let T be a minimal connected spanning subgraph of G. Okay, and our goal, okay, is to show that okay, T is a tree. Okay, so minimal connector subgraph means, like a spanning subgraph means, okay, this particular subgraph, it contains all the vertices of G, and that is a minimal one. Minimal one means if you delete one edge, it will become disconnected. So let's consider such a subgraph, and let T be a minimal connected spanning subgraph of G. Okay, every graph contains okay, such a subgraph. Okay, and our goal is to show that T is a tree. So if we are able to show that T is connected and T is acyclic, then we are done. Okay, that's what we are going to do here. Okay, so here you can see very easily see that this T is connected. So by the definition, and here we define T to be a minimal connected spanning subgraph of G. Okay, so that says T is connected. So only need to show that T is acyclic. So by the definition of T, so the T is defined to be a minimally connected spanning subgraph of G. Okay, so by the definition of T, for any edge G, okay, so if you remove any edge from this T, so since it is a minimally connected one, the graph will become disconnected. Okay, so for any edge E in T, and if you delete that edge, okay, from the graph, if you remove that edge from this minimally connected spanning subgraph of G, then okay, this T will become disconnected. Okay, is disconnected. So that is true for any edge in this tree. Okay, and that says okay, this particular thing is a cut edge in T. Okay, so therefore E is a cut edge or bridge in T. Okay, and next we are going to use this theorem. So an edge E of a connected graph, so we already know that particular tree is connected and is a cut edge if and only if E is not on any cycle of G. Okay, okay, so we are going to invoke that theorem. So an edge E of a connected graph G is a cut edge, okay, if and only if E is not on any cycle, okay, any cycle of G. Okay, and that says okay, this particular edge E is not on any cycle of T. Okay, since T is a cut, okay, since this E is a cut edge, and we chose this E to be an edge in this minimally connected spanning subgraph of G. Okay, okay, therefore E is not on any cycle of T. Okay, and that says okay, T is acyclic. Okay, and moreover we define T to be a minimally connected spanning subgraph. Okay, so moreover T is connected. So here we have this tree T, and T is acyclic. Okay, T is acyclic and T is connected. Okay, and that says therefore T is a tree. Okay, and we define T to be the minimally connected spanning subgraph of G. So it spans all the vertices. So that says okay, T is a spanning tree of G. So hence T is a spanning tree of G. Okay, so that's it. That's a proof. It's a very simple proof. Okay, so let's go into a corollary of this statement. Okay, so that says if G is a connected graph on n vertices and m edges, then the number of edges is always greater than or equal to n minus 1. Okay, so you can see that from this example. So if you look into this particular graph, you can see that we have 1, 2, 3, 4, 5, 6 vertices. Okay, so n is equal to 6 and m is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 is greater than 6. Okay, so anyway, this spanning tree, it has to have n minus 1 edges. Okay, so it contains n vertices. Okay, so a tree with n vertices has n minus 1 edges. Okay, so it could have more than that. Okay, that's the indication behind the proof for this statement. Okay, so let's go and prove this statement. So it's a very simple proof. So let G be a connected graph on n vertices and m edges. Okay, by the previous theorem we know that okay, every connected graph has a spanning tree. So we know every connected graph has a spanning tree. Okay, so therefore this graph G is a connected one, right? It has a spanning tree. And let's call that tree T. Okay, and therefore since T is a spanning tree, T has n vertices. Okay, and since it is a tree, okay, it has n minus 1 edges. Okay, so it could have more edges. Okay, and that says hence okay, number of edges is greater than or equal to n minus 1. Okay, and that's the proof. That's also a very simple proof. Okay, so let's look into some more terms related to spanning trees. So the branch and chord edges with respect to a spanning tree. Okay, so this is with respect to a spanning tree of a graph. Okay, that says a graph could have many spanning trees, and these are defined. The branch and chord edges, okay, are defined with respect to a spanning tree. So this is the definition of what is called a branch. An edge, okay, in a spanning tree okay, T is called a branch of T. And an edge of G Okay, that is not in a given spanning tree. Okay, T is called a chord. Okay, so this is how we define this branch and chord. Okay, and here the most important, so here an edge of that graph that is not in the given spanning tree is called a chord. Okay, let me give an example. So let's consider this particular graph G, and let's consider this spanning tree, okay, which is highlighted in blue. Okay, so here we can see that these edges B1, B2, B3 up to B7. Okay, B1, B2, B3, B4, B5, B6, B7. Okay, so these edges, they are part of this spanning tree. Okay, so here, okay, these edges B1, B2, B3, B4, B5, B6, B7. Okay, they are called branch edges. Okay, and the remaining edges, okay, C1, C2 up to C7. Okay, so they are called chord edges. Okay, so this is how we define branch edges and chord edges. And here one thing to remember is that, okay, these edges, branch edges and chord edges, are defined with respect to a spanning tree. So if you have a different spanning tree, then the branch edges and the chord edges, okay, may be different. Okay, so let me write down that here. So here, so note that, okay, the branch, okay, the branches and the branch edges and chord edges, okay, they are defined only with respect to a particular spanning tree. With respect to a given spanning tree. So a graph could have many spanning trees, and with respect to that a particular spanning tree, okay, we define the branch edges and chord edges. Okay, so I think that definition is clear. Definition of a branch and chord edges with respect to a spanning tree of a graph. Okay, and here again we can see one important thing here. If the number of edges, number of vertices is n, okay, in the spanning tree we have 7 edges. Okay, so that says the number of chord edges will be like 14 minus 7. Okay, so we can see that from here. Okay, here we have number of branch edges is 7, and number of chord edges will be equal to total number of edges, which is 14 minus 7. Okay, where 7 is the number of edges in the spanning tree. Okay, so let's go on to that. Okay, so this statement says something about the number of chords, okay, number of chords in a graph with a spanning tree. So the statement reads as follows: with respect to any of its spanning tree, a connected graph on n vertices and m edges has n minus 1 tree branches. Okay, so the tree branches corresponds to the number of edges in the spanning tree. So since it is a spanning tree with, and the spanning tree has n vertices, number of edges will be n minus 1. Okay, so it has n minus 1 tree branches and m minus n minus 1, which is equal to m minus n plus 1 chords. Okay, so let's go and prove this one. So the proof is straightforward here. So let G be a connected graph. With n vertices and m edges. Okay, from the previous theorem we know that since the graph is connected, it has a spanning tree. Okay, so let T be a spanning tree. Okay, since T is a spanning tree, T contains, okay, since T is a spanning tree, okay, T has n vertices, okay, and since it is a tree, it has n minus 1 edges. Okay, so the edges in a spanning tree corresponds to the branch edges, so it has n minus 1 edges. Okay, and so the number of chords, okay, that's the remaining edges in that graph. Okay, after subtracting this n minus 1 from the number of edges. Okay, so the number of chords in G is equal to m minus the number of branch edges. Okay, number of branch edges is n minus 1, so it is nothing but m minus n plus 1. Okay, so that's the proof. Okay, so we can see that with respect to any of its spanning tree, a connected graph G on n vertices has m edges and m edges has n minus 1 tree branches and m minus n plus 1 chords. Okay, so now it is another term related to a graph. It's called the rank and nullity. Okay, so let me give the definition of rank and nullity. Okay, let G be a graph with n vertices, okay, m edges and k components. Okay, so these terms rank and nullity, they relates the number of vertices, number of edges and the components in the graph. Okay, so these two terms are very important to graph. Okay, so this relates number of vertices, number of edges and number of components in the graph. Okay, so the rank, okay, denoted by R, and the nullity, okay, denoted by the Greek symbol mu, okay, of that graph G are defined as, okay, so R equal to n minus k and mu is equal to m minus n plus k. Okay, so this is how we define the rank and nullity of a graph. So let G be a graph with n vertices, n edges and k components. The rank R and the nullity denoted by this Greek letter mu of G are defined as, so rank will be equal to n minus the number of vertices minus the number of components in that graph, and mu is m minus this quantity R. So here again you can see that this is nothing but m minus R. Okay, so let me give an example of this. So if you look into this particular graph, the number of vertices here is 8, the 1, 2, 3, 4, 5, 6, 7, 8, and number of edges is 14, and here the number of components. Okay. that k here is 1, so it's a connected graph. So that says the rank, okay, R of this graph is n minus 1. Okay, so that in this case, since the graph is connected, that corresponds to the number of branch edges. Okay, and the nullity of this graph, okay, measured not by mu, okay, it is nothing but m minus r. Okay, so here r is 7, so that says the nullity of this graph is 14 minus 7, which is equal to 7. Okay, and one important thing to see here is that, okay, if you add the rank and nullity, you get the number of edges. Okay, 7 plus 7 is 14. Okay, so let's look into one more example. So let's consider this disconnected graph. Okay, here the number of vertices is 60, number of edges is 70, and the number of components is 3. Okay, for this graph, so here this, okay, blue subgraphs corresponds to a spanning forest. Okay, so here the rank of this graph will be equal to, okay, n minus k, so n is 16, 16 minus 3, which is 30. Okay, and the nullity is m minus r. So here m is 70. Okay, and okay, 17 minus r is 30. Okay, and that is equal to 4. Okay, so here if you look into this particular graph, we can see that this highlight blue subgraph corresponds to spanning forest. Okay, so this 13 corresponds to the number of branch edges, okay, in this forest. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so this corresponds to the branch edges in this forest, and this 4 corresponds to the chord edges, okay, in this forest. So here the chord edges is 4, and those are 1, 2, 3, and 4. Okay, so that's how these terms are related. Okay, so let's go and write something here. So here the rank is defined to be the number of vertices minus number of components, and the nullity is the number of edges minus the rank of that graph. Okay, so here very easily we can see that if the graph is connected, okay, the rank of a connected graph, okay, that is going to be equal to, so we have one component there, n minus 1. So that's what we saw here. The rank of this graph is a connected one, that is equal to 7, and that 7 corresponds to the branch edges of a spanning tree in that graph. Okay, and here, okay, again we can observe some more thing here. So as I said, the rank of G is the number of branches in any spanning tree. Okay, so let me write down. So here we can see that the rank of a graph G is equal to number of branches in any spanning tree. So if the graph is not connected, that corresponds to the number of branches in a spanning forest. Okay, and again we can see that the nullity of G, okay, of the graph is equal to the number of chords in G. So that's what we saw in this example, right? This 13 corresponds to the number of branches in this forest, and this 4, which is equal to nullity, that corresponds to number of chords. Okay, and again we can see that if you add these two terms together, okay, so we can very easily see that if you add this rank and nullity, okay, you get the number of edges in G. Okay, so you can very easily see from here. So 13 plus 4 is 17, and 17 is nothing but the number of edges in that graph. Okay, so this is how we define the rank and nullity of a graph. Okay, so let's look into one more property of a spanning tree. Okay, and this reads as follows: let T be a spanning tree of a connected graph G, and let E be an edge in G. Okay, and it be in G, not in G. So that says E corresponds to a chord in that graph. Okay, then T plus E contains a unique cycle. Okay, so if we add this edge E back to that tree, then anyway you will get a cycle, and that cycle contains, and okay, this particular thing, this graph contains a unique cycle, and that cycle will be a unique one. Okay, so let's go and prove this one. Okay, so we are given that T is a spanning tree of a connected graph. Okay, so let T be a spanning tree of a connected graph G. Okay, and E connecting U and B, an edge of G. Okay, not in T. So that says E is a chord edge. Okay, and since T is a spanning tree, okay, we know that T is acyclic. Okay, since T is a spanning tree, okay, we know that T is acyclic. Okay, and that says every cycle in T plus E contains an edge. Okay, since T is acyclic, then if you add this edge back to that spanning tree, then every cycle in T contains the edge G. Okay, then we have to prove that it is a unique one. Okay, and again we can see that, okay, since every cycle in this particular thing, every cycle in T plus E contains the edge. Okay, there is a one-to-one correspondence between the cycles. Cycles in T plus E and a path from U to V. Okay, so since this edge connects U and V, okay, so that says hence there exists a one-to-one correspondence between the cycles in T plus C and this UV path in T. Again, from the properties of tree, we know that in a tree, okay, there is a unique path. Okay, there is a unique path between any two vertices. So it is also true for these two vertices. Okay, we know that in a tree there is a unique UV path. Okay, and since every cycle in T plus C there exists a one-to-one correspondence between the cycles and this UV path. Okay, and since the path is unique, okay, that says that cycle is also going to be unique. Okay, and that's a proof. So hence there is a unique cycle in T plus E. Okay, and that's a proof. So here we started something like this. We have the spanning tree of a graph G and E, a chord edge. So we know that T is acyclic. Okay, so that says since T is acyclic, okay, once you add this edge, okay, the graph will become cyclic, and every cycle in T plus E contains the edge E. Okay, and again we can also see that there exists a one-to-one correspondence between, okay, the cycles in T and this UV path in T, because we chose E in that way. Okay, E is the edge connecting U and V. Okay, and this all the cycles contains this particular edge, right? So that's it. There is a one-to-one correspondence between the cycles in T plus E and UV path in T. And since we are dealing with a tree, so we know that there is a unique path between two vertices. Okay, in any tree. Okay, and since the path between U and V is unique, okay, and that says the cycle that includes UV, okay, that edge is must also be unique. Okay, and that says there is a unique cycle in T. Okay, and that's it. Okay, so that's it. That's all for this video. Okay, and we continue with the discussion spanning tree in the next video.